All right, problem set 20. So this first question here says that f of x equals 5 cosine of x for 0 to pi over 2. And they want us to complete our lower sum and our upper sum for the function with the given partition. Okay, so we first might just kind of sketch this out so we can get a picture for what this looks like. I know cosine typically looks something like this, right? Where this would be 2 pi, because that's its period. This would be pi over 2. So since we're only going up to pi over 2 from 0, we're just going to mark that pi over 2 there. I know at pi over 2, it's right there. At 0, well, it's a 5 cosine, so it would normally be at 1. Here it's going to be at 5. So I'm going to mark that, and I know it's going to look something like this. It doesn't have to be perfect. It's just to get us a picture of kind of what's going to be lower and upper when we're looking at those sums. So for that lower sum there, obviously we've got, well, we should go ahead and label the spots of our partition. It's going to look something like this. Okay, there we go. Now we've got every piece labeled. So for that lower sum, I see that, oh, this should be higher. So it doesn't curve like that. It curves like that on here. Let me just fix that so it's not confusing. Just visually. It's tough to do. But so here, with that lower sum, so we want to underestimate, kind of like what we see down here. So I know obviously if I use my point at 0, that's going to end up coming over it. So that would be an overestimate. So first we're going to figure out this here. And we want to figure out this area. Next, we're going to come down to the next lowest one and go like that. And so on. So that we would get that there. And of course this rectangle is just like that there. So this, of course, is going to be the area. So it's going to be pi over 6 times whatever cosine of pi over 6 is. So I know that my lower sum is going to start off with pi over 6 times whatever 5 cosine of pi over 6 is. And then I'm going to have whatever this distance is times cosine of 5 cosine of pi over 4. So let's figure out the distance between pi over 6 and pi over 4. Common denominator is 12, so it'd be 2 pi over 6 over, sorry, not 2 pi over 6, 2 pi over 12. That's what that turns into. And a 3 pi over 12. Sorry if you can hear my dog barking. Okay. And that's going to end up, of course, being a distance of just pi over 12. And that's going to be that same distance here, which you can always double check on your own. So it's going to be plus, and you've got pi over 12 times, again, that 5 cosine of pi over 4, plus, and this is also a distance of pi over 12, so pi over 12 times 5 cosine of, now the lower one's pi over 3. And then this, of course, we know is at 0, so we don't really need to calculate that, but you always could. You could just do that distance of, I think that's the distance of pi over 6, so pi over 6 plus 5 cosine of pi over 2, which just equates to 0, so we don't really care. Okay, now, now we just have to figure this out. Obviously, we should know our unit circle pretty well by now, so we're going from 0 to pi over 2, pi over 4, pi over 6, pi over 3, and of course that's going to be, we're going to put our coordinates, of course, because those are what we are going to be using. Okay. So cosine at pi over 6 is that square root of 3 over 2. So it's going to be 5 times square root of 3 over 2 times that pi over 6. So that's going to be 5 pi square root of 3 over 6 times 2 is 12. I don't know that we can reduce that any more than it is, but we'll just leave that as it is right now. And then plus, over here we've got cosine of pi over 4, so it's going to be pi over 12 times 5 times cosine of pi over 4 is square root of 2 over 2. So that's going to be 5 pi square root of 2 over 24. And then our next one is another pi over 12 times 5 times cosine of pi over 3 is 1/2. So it's going to be 5 pi over 24. Obviously, we've got easy common denominator here. Just make this one over 24. So it's going to be 10 pi square root of 3 over 24 because we're just doubling that. Plus this and plus this is going to be, let's see, that's going to be, I don't know that we can really combine them together. All over 24. And I would just put that into your calculator maybe to type that in. So let's see what that would be. So 10 pi times the square root of 3 plus 5 pi square root of 2 plus 5 pi divided by 24, and that's going to be roughly this here. Okay. Now we need to compute that upper sum, right? So it's going to be the exact same thing we did here, except instead of underestimating, we want to overestimate. So I'm going to erase those there. So now I'm going to start with whatever is the highest. Well, obviously the highest over here is going to be that. Okay. And then that, right? And then this. And then this time, we actually do go over here. This is our nice overestimate. I cannot draw a straight line, apparently. There we go. So I can remember this distance is pi over 12, because that still matters to us. Now, this area is going to be pi over 6 times this height of, well, we just know that that's 5, don't we? But 5 cosine of 0, which is just 5. So that first part of our upper sum is pi over 6 times 5, which we can just write as 5 pi over 6. The next one, slightly less pretty, it's going to be pi over 12 times 5 cosine of pi over 6. Next up, we've got another pi over 12 times 5 cosine of this next higher one, which is pi over 4. And then we've got this distance of pi over 6 times 5 cosine of pi over 3. Okay, so now looking at our unit circle again, so it's going to be 5 pi over 6 plus, well, cosine of pi over 6 is square root of 3 over 2. So it's going to be 5 pi square root of 3. 12 times 2 is 24. Next up, we've got this cosine of pi over 4, square root of 2 over 2. So it's going to be 5 pi square root of 2 over 24. And then that's going to be 1/2. So 5 pi over 12. And again, we can find that common denominator, put them together. So it's going to be 20 pi over 6. Oh, no, not over 24, sorry. Plus this. And then that. And these actually do combine quite nicely. That's lucky. So it's a 30 pi over 24 plus both of these, which is then just 30 pi plus 5 pi square root of 3 plus 5 pi square root of 2 all over 24. And again, we're going to just go ahead and plug that into our calculator just because I don't know what formatting looks like. So 30 pi plus 5 pi square roots of 3 plus 5 pi square roots of 2 divided by 24. And our upper estimate looks about like this. So I know that the actual area under the curve, or the actual integral there, would be somewhere between these two numbers, because this is our lower estimate and our upper estimate. Okay, oops. Let me just erase some of this so we've got lots of space for the next one. Okay. All right. Up next, number 2, same thing, except now they've kind of given us the graph because it's a little bit different. So we've got this function of 2 sine of 2/3 x, and you can see here we've got 3 pi, and obviously like 3 pi over 2, etc. So first we need to identify which one is our lower sum and which one is our upper sum. So it looks like this one's going to be our lower sum because I can see that we are underestimating. And I know it looks a little bit different, right? It looks like we're overestimating if the second half here, but we aren't. And the reason that is because we are going further into the negatives, and obviously our negatives are smaller. So adding on those negatives is going to be just furthering that underestimate. Same thing over here, we're overestimating, and so we're staying, again, above that curve and not blocking that out. Okay, so let's start. We know our lower sum is going to be based on this. So obviously this is 3 pi over 4, which means that this is 3 pi over 8, right? Just cut that in half. And this is whatever those are added together. Let's see, 6 pi over 8, 9 pi over 8, 9 pi over 8. Seems accurate. Right? And then another 3 pi over 8 would be 12 pi over 8, which does reduce to 3 pi over 2. Okay, good. Yeah, this is looking good. So first we see that this is obviously the height at 3 pi over 8. So I'm going to figure out this distance is 3 pi over 8. So it's 3 pi over 8 times, now this height, right, because we're just finding the, oh, no, wrong. I did that wrong. This distance doesn't matter because obviously this is 0 with our lower sum. So we're looking at this distance, which is also 3 pi over 8, but just didn't want to be too confusing there. So this 3 pi over 8 times this height, which is 2 sine of 2/3 times 3 pi over 8. And we'll reduce that more after we get the rest set up. This next one is going to be, obviously it looks like that same thing. So I'm just going to mark that we can just double this because there's 2 of it. Coming down, then this part is 0, and then we've got this here, which goes down to this height here, which is whatever 3 pi over 2 plus 3 pi over 8 is. That's an interesting distance. Shoot. 3 pi over 2, so it's 12 pi over 8 plus 3 pi over 8, 15 pi over 8. Okay. 15 pi over 8 times 2 sine 2/3 times 15 pi over 8. And it may not be obvious, but this is going to be that same thing. So again, I'm going to mark a times 2. You could go ahead and write each one of these rectangles out, but I just kind of recognize that these rectangles are going to be the same area. So I'm just going to multiply that by 2 to make it a little easier on myself. And then we've just got these 2 rectangles there, which are also equal. And at the height of this 9 pi over 4 there. So that's going to be another distance of, oh, you know what? This shouldn't have been a 5 pi over 8 because that was what this is, not the distance. Or sorry, so that distance should still be 3 pi over 8. And then again, this distance is 3 pi over 8, but our height that we're plugging in there is 9 pi over 2. So another 3 pi over 8 times 2 sine 2/3 times 9 pi over 4. And technically, and again, this is actually times 2 because it's these two rectangles. And technically here, I could have actually factored this out since they are, all those subdivisions are equal in length. So actually, we might do that. That sounds like that's a little easier on us. So 3 pi over 8. And then it's just 2 of this. So I'm actually going to apply that to, so times 2. 2 is going to be 4 sine of, let's actually reduce that now. So it's going to be 6 pi over 24, which just reduces to pi over 4. Okay, then we've got this one over here, another times 2, so plus 4 sine, and now that's going to be 30 pi over 24, which we can reduce to 15 pi over 12, or then 5 pi over 4. Okay, and then another 4 sine, and then that's going to be 18 pi over 12, or 9 pi over 6, 3 pi over 2, I think. Looks like that makes sense. Okay, now, again, going back to our unit circle, I'll actually just write that out a little bit over here. Yeah, so we've got this here. And we've got nothing over 6 or over 3, so we're really just going to focus on these here. Okay, so now we've got 4 times sine of pi over 4. Sine of pi over 4 is square root of 2 over 2. So it's going to be 4 square root of 2 over 2, or just 2 square root of 2. Okay, plus, now I've got 5 pi over 4 here, which is going to be a negative sign, right? So it's going to be negative square root of 2 over 2. So it's going to be 4 times negative square root of 2 over 2, which is then just negative 2 square root of 2. And then we've got sine at this 3 pi over 2. Did I factor that correctly? 9 pi over 6. Yeah. Okay. And so then that's going to be here. But that doesn't make sense given the distance between these. Did I make a mistake? Oh, no, it's fine. I just skipped over. I'm doing it times 2. Okay, that's fine. So then this is that there. So it's going to be plus 4 times negative 1, or negative 4. Obviously, these two cancel out. So then it's just 3 pi over 8 times negative 4, which is then negative 12 pi over 8, or negative 3 pi over 2. So that lower sum there is going to be negative 3 pi over 2. Okay, gonna erase all this now so we've got space to do that upper sum. Okay. And the upper sum is just the same thing, except we're going off the higher bits. So we've got this here, which we said was a distance of 3 pi over 8. Okay, and then that's going to be at the height of that. So we've got, and again, we can factor out that 3 pi over 8 because they're all going to be that same distance. So then it's just this height here, which is 2 sine 2/3 times this height of 3 pi over 8. Next up, oh, and I actually see that that's going to be same thing there. So again, I'm going to double that. And then plus, same deal, except now I've got different height. So 2 sine of times 3 pi over 4. And again, there's 2 of these, so I'm going to double it just for efficiency's sake. And then we've just got these 2 rectangles, which are also clearly equivalent. And these are at these heights, which is not that 9 pi over 4. So now we need to identify this. I remember I said this was 15 pi over 8, I think. Yeah, it was 15 pi over 8, so I can plug that in. 15 pi over 8. And then, of course, double it. And now we just work with this. So it's 3 pi over 8 times 4 sine of, it's going to be 6 pi over 24 again, or just pi over 4, plus 4 sine of, that's going to be 6 pi over 12, or just pi over 2, plus 4 sine, it's going to be 30 pi over 24, or a 15 pi over 12, which we then reduce to 3 pi over 2. Okay. Sorry my dogs are barking so much in this one. My parents aren't home, so they're on edge right now. Now, just plug in those values. So it's 4 times sine of pi over 4, which is just going to be square root 2 over 2, or just 2 square root of 2, plus 4 times sine of pi over 2. Sine of pi over 2 is 1, so it's just plus 4. And plus 4 sine of 3 pi over 2. 3 pi over 2 is negative 1, so it's negative 4. These cancel, and we get 3 pi times this, so it's going to be 6 pi square root of 2 over 8, or 3 pi square root of 2, 4. And that is our upper sum. I feel like I may have made a mistake, but I think you get the general gist even if I did. Just get the idea there. Let's take a look at number 3 now. We want to compute the right and left sums for the indicated partition and function. Our right and left sums are different from our lower and upper sum, just because whether or not they are an overestimate or an underestimate depends on the curve. But that does not affect like what we're calculating if it's just a right and a left sum. So I gave us 2 of this graph here to make it a little easier for us to draw out. So our left sum is obviously going to be based on the height of whatever at the left, so it's going to look like that. And our right sum is going to be based on the height of whatever at the right, so it's going to look more like this. Okay. In this case, our right sum is an underestimate, but if we had a function like this, of course my right sum would be an underestimate over here, but it would be an overestimate elsewhere. Oh, no, it would be an underestimate on this side. But then that right sum would be an overestimate on this side, which is why we consider that lower sum and that upper sum different from our left and right sums. Okay, so in this case they say p equals 5, so that's going to be y equals 5 over x minus 1/2. Okay, so it's going to be a distance of 1 for all of these times the height here. This height is going to be 5 over 1 minus 1/2, so it's going to be 5 minus 1/2. Okay, And then that's going to be the area here. So it's 5 minus 1/2, which is just 4.5. This next one is going to be another distance of 1. And that height is going to be 5/2 minus 1/2, which is 2.5 minus 1/2, or just 2. Next up, another distance of 1. Now the height is 5/3 minus 1/2, which is just a little trickier to work with. I'm going to find a common denominator there, so it's going to be 10/6 minus 3/6. It's going to be 7/6, or 1 1/6. And then this one is another distance of 1, a height of 5/4 minus 1/2. You'll notice, obviously, I'm just plugging in each of these numbers into this function to figure out those heights, because each point is along that curve. And that's going to be 5/4 minus 2/4, which is 3/4. Okay, so my left sum is all of these areas added up together. So 4.5 plus 2 is 6.5, plus 3/4 is going to be, let's see, oops, that's going to be 5/4, or just another 1 1/4. And then we just have to add that 1 1/6. So it's going to be 8 1/4 plus 1/6. Let's find a common denominator. 8 3/12 plus 2/12. That's going to be 8 5/12. Okay. Now to do our right sum, which is the exact same thing, except now we're looking at the point on the right. So this first distance is again 1, but now the height is, oh, it's not writing. Why is it doing that? Okay, that's weird. Okay, that was weird. I didn't like that. But now it's going to be the height from plugging in these right values. Okay, so this first one is going to be distance of 1, and then 5/2 minus 1/2, which we already said was 2. And this next one's going to be 1, except now it's 5/3 minus 1/2, which we already said was 1 1/6. And then it's 5/4 minus 1/2, which we said was 3/4, except now we've just got this last one, which we didn't already figure out. So it's going to be 5/5 minus 1/2, which is just 1 minus 1/2, or just 1/2. So now we add those all up together to get our right sum. So let's see that 2 plus 1 1/6, this is going to be 3 1/6. That 3/4 plus 1/2 is going to be 1 1/4. So that's going to be 4, and that 1/6 is 2/12, 3/12, so 4 5/12. Okay, on to number 4. So we're given another function, and we want to compute that lower and upper sums again. So they've given us a partition here, and we can see from looking at this that they're all 1/2 apart, so we can actually just factor that out like before. So it's going to be, let's start with that lower sum. It's going to be 1/2, and then factor all that out. And we know x to the 4th looks something like this on our graph. And it changes at 0, so we'll keep that in mind. So then, looking at this, everything over here, we should do a right sum to estimate, so it's going to look like this, right? And everything over here, we should use a left sum to estimate, so it's going to look like this, because the point that's on the line is to the left. So first, gonna do that that right sum for these 3 points there, or technically 4. I'm gonna actually sketch out that graph a little bit larger so we can see it a little clearer, what's happening here. So that's going to look something like that. It's not quite just our parabola, but it's close. So we've got 0 to 1/2. We'll say it's there. 1, yeah, 1/2, 1, 3/2, -1/2, -1, -3/2. Okay, so again, we're going to use the right sum over here, which means that this part's 0, and then it's up here, and then here. We're going to use the left sum over here, so again, this part's 0. I've got that. And theoretically, because this is an even function and it just reflects about the y-axis, these should be equivalent. So really, we could just find one of these sides and then double it. And actually, we might do that. Which would undo kind of that 1/2 there, because if we double all of it, that's going to be 1/2 times 2, which is just 1. So it's just 1 times everything. So let's just find our right sum then, and we'll double that. So let's see. So this is going to be, I said that this was -1/2, -1, -3/2. Okay, so this is the height of that -1/2, so plug that in there. So it's 1/2, -1/2 to the 4th, and then the next bit's going to be 1/2 times -1 to the 4th. Okay, that's going to be 1/2 times, well, 1/2 to the 4th. I know 2 to the 4th is 16. So it's going to look like that. Plus 1/2, which is then 1/32 plus 1/2, which is 17/32. That, I don't know. I think that's right. I'll have to double check that at some point. And then for our upper sum, of course, we're going to do this graph a little differently. Of course, the actual graph of the function stays the same. Why won't it undo things? It's undoing the wrong things. I don't like that. Okay. And it looks something like that. Okay. So 0, we said 1/2, 1, 3/2. Obviously, now we want that overestimate, so I'm going to use a right sum on this side and a left sum on the other side. Or, again, since this is an even function, it's going to be the same areas on each side. So I'm just going to find this right sum here and double it. So it's a distance of 1/2. Doubling it cancels it out. So now it's just this height here, which is 1/2, 3/2 to the 4th, plus 1/2, 1 to the 4th, plus 1/2, plus 1/2 to the 4th. Okay, 3/2 to the 4th is a little tricky, just because I don't know what 3 to the 4th, yes I do, it's 81. It's going to be times 81 over 16 plus just 1/2 plus 1/2 times 1 over 16, which gets us 81/32 plus 1/2 is going to be 16/32 plus 1/32. So let's see, that's going to be 97, 98 30 and I think 32 times 3 is 96. So this is going to be 3 and 2 30 or 3 and 1 16th. That's a big difference. And sometimes they are, but it just makes me wonder if I messed up somewhere. But that's the general idea, right? Let's try number 5 now. Same deal. They let us use a calculator for this one because it gets pretty ugly. So f of x equals x to the 1/3, or just the cube root of x. And I know if I was to kind of graph that, we're going from 0 to 2. I know that that's going to look like something like that, right? So makes it, just being able to visualize that helps us figure out what our lower and upper sums look like. So it's split up into, it goes from 2, 1, it's got that 1/3, 2/3, 4/3, 5/3, there we go. And that's our partition. So I see that they're all 1/3 apart. That makes it easy on us. So again, we're just going to factor that out. 1/3. And then it is, that lower sum is going to be a left sum for us. So it's going to look something like this. And once you kind of get the gist of that, you don't even really have to draw it out all the time. We just know it's going to be all of these except this last one, right? Because it's going to end up like that. So let's go ahead. I know it's going to be plugging in the 0 there, which is just going to be 0. I just graphed this wrong. That's okay. So it's going to be 0 plus plugging that 1/3. It's going to be that cube root of 1/3 plus cube root of 2/3 plus cube root of 1 plus cube root of 4/3. Oops. Plus cube root of 5/3, and again, we aren't including this 2 because this is a left sum, so we don't end up reaching that. And then I would just plug this part into your calculator. So it's going to be, yeah, I'm just going to plug that into the calculator. So let's see. Like cube root of 1/3 plus cube root of 2/3 plus cube root of 1, which is just 1, plus cube root of 4/3 plus cube root of 5/3, and then all times 1/3 or just divided by 3, and that gives us a lower sum that looks something like this. Oh, and it says round to the nearest thousandth, so I don't even have to go out that far. That's going to end up just being that. Okay. Up next, we've got our upper sum, which is looking at this just the exact opposite, right? We're going to use a right sum here for the whole thing, which means we're not going to use that one, but we are going to make our way to using this height here. So again, factor out that 1/3. And now I've got cube root of 1/3 plus cube root of 2/3 plus 1 plus cube root of 4/3 plus cube root of 5/3 plus cube root of 2. And again, we plug that into our calculator. So cube root of 1/3 plus cube root of 2/3 plus cube root of 4/3 plus 1, I forgot that, plus cube root of 5/3 plus cube root of 2, and then again times 1/3 or just divided by 3, round to the nearest thousandth, and that's going to be something like that. Boom. Okay. Next up, same deal, except now we've got a sine function on our hands, and it goes from 0 to pi over 2. So, as we'll see here, you've got 0, pi over 2, pi over 4, and they've got the same partition as that one earlier, which obviously isn't an even partition, or an even length interval, so we can't just factor it out. And I see that it's a 2 sine, so I know sine of pi over 2 is typically 1, so it's going to be 2, and then plus a 1, so it's going to be all the way up to 3. I know it's going to look something like that. Okay. Getting that lower sum, I can see pretty clearly, is going to be using a left sum. So that lower sum, left sum, so it's going to be, oops, and I forgot that this is actually a plus 1, so it doesn't go all the way down to 0. Goes to 1. It starts about there. Ah. Okay, that looks pretty good. Okay, still going to be that left sum though, right? Because it's going to look something like that to be our underestimate. So that lower sum is a left sum here. So it's going to be 2 sine of 0, which is just 0, plus 1, which is 1, times this distance of pi over 6. So pi over 6 plus times 1 is 1, or just is pi over 6, sorry. Next up, we've got this distance, which earlier we determined was pi over 12, as is this. Okay. So now we've got pi over 12 times 2 sine of pi over 6, because remember it's a left sum for this underestimate, plus 1. Next up, we've got this one here. So plus pi over 12 times 2 sine pi over 4 plus 1. And then that final left sum there is going to be plus, and this is a distance of pi over 6. So pi over 6 times 2 sine of pi over 3 plus 1. Actually, I see I've got these plus 1s here. I can just pull those out. So it's 3, because it's 1 plus 1 plus 1, plus pi over 6, plus, well, sine at pi over 6 is 1/2, so it's 2 times 1/2, which is 1. 1 times pi over 12 is just pi over 12. Next, we've got pi over 12 times 2 sine pi over 4. Well, sine of pi over 4 is square root of 2 over 2 times 2 times pi over 12 is this. Next up, we've got this one here. So that's pi over 6 times 2 sine pi over 3. Sine at pi over 3 is that square root of 2 over 2, or square root of 3 over 2, sorry, times 2. Those cancel. So then it's just pi square root of 3 over 6. Okay? And we already pulled out those plus 1s, put them in the front so they're nice and easy to reach. Next up, that's going to be 3 plus, well, this is 2 pi over 12. So that's going to be 3 pi over 12, which is just pi over 4. And then I can combine these. Let's see. So that's pi square root of 2 plus 2 pi square root of 3 over 12. And I actually could have kept this over 12. That was 3 pi over 12. So then I can just put that up also in this numerator. Okay. And yeah, we're just going to plug that into our calculator, and that is our lower sum. So let's see, we've got 3 pi plus pi square root of 2 plus 2 pi square root of 3 divided by 12 plus 3 wholes. Okay, that gives us an underestimate of this. We round to the nearest thousandth, so that's that. Okay, our upper estimate is going to be same deal once again. It's all pretty much the same topic, same practice really, except now we're going to use that right sum because I see that that's going to be an overestimate. So that is going to be, well, again, I know that I'm going to have several plus 1s, so let's see. It's going to be sine of this plus 1, sine of this plus 1, sine of this plus 1, sine of this plus 1. So it's going to be 4 plus 1s, which I can just pull out as a 4 in the front, and now we can ignore them. Remember that f of x equals 2 sine of x plus 1. We're now ignoring that plus 1 because we've just done them all. So it's going to be 4 plus this first distance of pi over 6 times sine of pi over 6. Sine of pi over 6 is, or times 2 sine of pi over 6. Sine of pi over 6 is 1/2. 2 times 1/2 is 1, so it's just pi over 6. Next up is pi over 12 times 2 sine of pi over 4. So it's square root of 2 over 2 times 2, or just square root of 2. So there's that. Next up we've got this point here, which is another pi over 12, because that distance, remember, because we're just finding the area of this rectangle, times, well, sine of pi over 3 is a square root of 3 over 2, times 2 is just square root of 3. And then finally, we've got this last point here, so it's a distance of pi over 6, times 2 sine of 1/2, or pi over 2, sorry. Sine of pi over 2 is 1, 2 times 1 is 2. Okay, so now, and I'm gonna give this common denominator of 12 just so they're all over the same thing. That's going to be 2 pi over 6, or 4 pi over 12. And then I can combine these to be a nice 6 pi over 12. And since it's actually all over 12, I can just put those in that same numerator. And once again, plug that into calculator. So 6 pi plus pi square root of 2 plus pi square root of 3 divided by 12 plus 4, and remember round to the nearest thousandth here, so looks like this. Continuing on, we've got another one of these, and it goes out pretty far. This one's not a fun one. This one, I don't know exactly how they wanted us to use the calculator for this one, because they didn't fully instruct us, but I did figure out basically how to do like Riemann sums in calculator. So I'm actually going to do that here because this is a lot of subintervals. So we want to find this as well as this. And so if I was to kind of graph that out, our e to the x tends to look pretty exponential, does it not? Let me just graph that to double check. Want to be confident in it, obviously. Yeah, so we say 5 is about here because it's got that plus 5, and then it's going to look something like that. Oops. Okay. It's going to look something like that, right? So I know that my lower estimate I can find using a left sum once again. So going into my calculator, I'm probably gonna have to write this out so it's easy to follow. I have a TI-84. So if you don't have a TI-84, this might work on a TI-83. I haven't tested it, but I don't know about other calculators. If you don't have a TI-84, there's plenty of apps, obviously. There's free ones on, like, for your computer and for your phone. So, like, if you just want to use those, I would recommend it. So let's see, what were those steps that we took? Now I have to remember how I did it, because I did it the other day. Okay, so what we're going to do is we first, on our calculator, we press that second button, and then immediately press the stat button, and that's going to be, it's going to select this list part that's right above it in blue, or probably in blue, it's blue on my calculator. So you click that, and then you want to go over to that math tab, and click sum, which for me is the 5th one down. Oops. So you want to click sum, and then before doing anything with that, you then repeat this part here. So second stat and then this time you go to ops, or like operations, and go to sequence, or seek, which is also the fifth one down for me. And here, wants you to input, it's going to give you something that looks something like this. Okay. This expr right there, I don't know what that stands for, but that's just the function we're using. So in our case, that we're just going to type in that 2e to the x plus 5. The variable is x. Our starting point, since we're using a left sum for our lower estimate, it's going to be 0 here. And we know, since our step or our subintervals are 0.2, we know that using that left estimate, we're not going to get to this 2. We're only going to end up going up to this 1.8 when we're using that height there. So at end, I'm going to type in 1.8, and my step is a 0.2. And then if I press paste and then enter so it runs, that's going to give me something like this. That's just me rounding to the nearest thousandth. Now we're going to do those same steps, except we're going to do a right sum for our overestimate, right? So it's going to look something like this. So now our start is not going to be 0. It's instead going to be this first 0.2 here. And our end is going to be 2. But otherwise, exact same process. So we go to that sum. We go select the sequence. Okay, so this was, I typed in the wrong thing. Let me redo that, sorry. I didn't even type in the right equation. So 2e to the x plus 5, variable x, our start was 0, our end there was 1.8, and our step is 0.2. Wow, that's big. Oops, didn't mean to zoom out. And that gets me like this, actually. Whoops. Okay. Now we want to do the upper sum. So again, like I said, all those same steps. So go to sum, go to sequence, type in that equation, variable x. Our start now, like I said, is that 0.2, and our end is 2. Step is the same. I've got an overestimate of something like that. And that's it. And we'll use that more on the next homework too, I believe. But next up, now we've got some pretty short ones here. We want to find all the antiderivatives or integrals of this function here. So this is pretty simple, right? This is undoing that power rule for all of this. So add 1 to that exponent, so it's going to be x cubed. And I know I'd normally bring that in front, so it'd be 3 times whatever was here. So undoing that, I'm going to divide by 3. So I've got that coefficient in front of 9, which is just 3x cubed. And then minus, got that 3. And I'm going to add 1 to the exponent. So that gets to be squared. And then divide by our new exponent. And then plus 4. That's technically x to the 0. So I'm going to add 1. So it's just x to the 1. Or x. So what we got there is we got 3x cubed minus 3 halves x squared plus 4x plus c, because we don't know if there's an extra constant, and because this isn't a definite integral, we can't solve for that. We can't figure that out. So there may or may not be a constant, so we use that plus c, and this is all of our derivatives for that. Or all of our antiderivatives, sorry. This next one, same deal, except it's a little bit more abstract. Now we don't know what our exponent is. They're just giving us a variable for it. We know that it's probably a constant, so we're going to treat it like it's a constant exponent. So normally, if I've got this, well, undoing undoing that power rule, I'm going to add 1 to that exponent. So it gets to be that, and then we divide by the new exponent, right? Just like we were doing. And then of course this is a constant still, so it's n, and if it's a constant, we know we just put that x back on because, right, we're just adding that exponent on. So this is what that's going to look like. It's going to look something like that. I don't think we have to do a plus c for this. We might, but I'm just going to leave it like this right now. And boom. Now it says if the derivative of f of x equals this here, and f of 2 equals -5, what is the original function f of x? Well, so we want to take the derivative here, so I see that I've got a constant coefficient of -1/2 in front of my x, -3, because remember this is the exact same thing. So undoing my power rule, this is a power of 1, so I'm going to add an exponent, x of 2, and divide by 2. -1/2 divided by 2 is -1/4. That -3 is going to get -3x. We could do that plus c, but I know since we're going to be putting stuff in, it's not super obvious. No, we do want to do that plus c. Sorry, misspoke. Now, so I know that my f of x is going to look something like this because I just did my antiderivative there. So now I know f of 2 equals -5. So it's going to be -1/4, 2 squared, -3 of 2, plus c. So it's going to be -1/4 times 4 minus 6 plus c, which is just -1 minus 6 plus c equals -5. So -7 plus c equals -5, c equals 2. So it's going to be all of this except c is 2. So, oops, boom. And now, same exact thing, but for the next problem. So our derivative is e to 2x divided by 3, and we know that f of 0 equals 4. Well, I know that if I was to take the derivative of this, it would just be itself times the derivative of that top, right? So it's going to be 2/3 times that e to the 2x over 3, which means that going backwards, in order for it to just be this without any coefficient, taking the derivative, this would have to cancel out with whatever was in front of it beforehand. So in order to do that, we just flip it, obviously. And so that should be our integral there, and then of course a plus c. And we can double check that, right? If I take the derivative of this, that's going to be 3/2 times the derivative of the top, which is 2/3, times e to the 2x divided by 3. 3 cancels out, 2 cancels out, and it's just this by itself. Yep, so that checks out. So we know our f of x equals this, and I know f of 0 equals 4. So f of 0 is going to be 3/2 e to the, that's going to end up being 0 altogether up there, plus c equals 4. So anything to the power of 0 is 1, so it's just 3/2 plus c equals 4. Versus, I could rewrite that as 1.5. If I then subtract that from both sides, we get c equals 2.5. So our function is 3/2 e to the 2x divided by 3 plus 2.5. All right, and that is it for this one. This was not the worst, I think. I don't think it was too super long either, but I hope that everything I said made sense, and that this was helpful. Thank you for watching.